Thank you everybody for joining us today on this lovely winter day. I've got with me two of the more experienced professionals in the field of solar foundation design and solar racking design, Angelica Mendoza and Mariano Lulateri. I'll let them introduce themselves and tell you a little bit about themselves, but just wanted to speak a little bit about what gave us the inspiration for this webinar. As many of you know, the renewable energy sector is growing extensively in both Canada, the US, and abroad. And when working in some of the more northern regions of the United States and in Canada, there's some very unique considerations that need to be taken into consideration for the design of these systems. And in order to come up with a optimized system, it's extremely important that you have both sound engineering on both the foundation and racking side of things. And too many times I've seen in my career where the foundation engineer and the structural engineer have been out of sync, which resulted in not the most straightforward foundation designs or racking systems as it relates to specific site conditions. And we wanted to dive into some of those issues and challenges today. As I mentioned, we have two of the more experienced engineers in Canada and North America as it relates to designing these systems in cold climates. I'll start by handing it over to Mariano with Polar Racking, who is the Director of Engineering over there, and I'll let him maybe just briefly tell us a little bit about himself.
Thank you very much, Arash, and welcome everybody to this webinar. My name is Mariano Gualtieri. I'm the Engineering Director at Polar Racking. I've been with Polar Racking since 2021. And before that, been working for over 16 years on other solar PV or solar thermal application, always within the renewable sector. I hold a degree in industrial engineering and mechanical engineering, so I'm always incorporating or leverage the advantage of manufacturing processes into our design. As the director of engineering for Polar Racking, I oversee the department tasked from the day-to-day operations from engineering deliverables on all our awarded projects, as well as on the R&D front with testing, validation, and certification of the product as well. Now over to Angelica.
Thank you, Mariano. My name is Angelica Mendoza. I've been with PRI for over 6 years now. I graduated from Queen's University, where I did my bachelor's in geological engineering and my master's in geotechnical engineering. At PRI, I've been involved with solar projects from the start. So I've been involved in both small, both large solar developments with a combined of maybe over 2 gigawatts of sites already, doing detailed geotechnical investigations, foundation design, quality assurance reviews for racking support across sites in Canada and the US and Caribbean. I'm also a licensed engineer across multiple provinces in Canada.
Thank you very much, Angelica, Mariano. We're extremely lucky to have both these individuals with us. Before we get started, just a little bit of housekeeping. So our agenda for today, we will talk about, just give you an overview of Polar Racking and PRI engineering from our respective professionals, discuss environmental loads and frost uplift, and then discuss the requirements for designing and building robust racking solutions in northern or cold climates, looking at considerations as it relates to operation and maintenance. And we've also got 2 case studies for you that we're really excited to talk about. And finally, if there's any time left over, we will have a Q&A session, but we are happy to answer your questions as we go through the webinar. So please feel free to use the Q&A function at the bottom of your Zoom application. You can just type the questions directly into the chat and we would be happy to answer those questions for you. So I will hand it over back to Mariano, who will talk about polar racking.
Thank you. Thank you, Raj. Thanks, everyone. And so let me introduce the Polar Racking, the company. So Polar Racking has been around for 16 years already in operation. It started as a rooftop solution for the market and quickly evolved into adding fixed steel into the portfolio, carports, single axis tracker, and agrivoltaics application as well. Our goal is always to deliver the best product possible at the best price. And to achieve this, we have three main resources, which is in-house engineering, from geotechnical to structurals to design engineering. So we got the people, then we got the tools, so software, different wind tunnel studies to better understand the product, or whether it's bifacial gain on the modules, right? And how we can embed these into our calculations. And last but not least is the experience with over 4 gigawatts of product install, build, deliver, and currently producing energy on the field. To better serve our customer, we also have different manufacturing partners across the multiple countries, the US, we have in Canada as well, and Asia. So, of course, we are compliant with US domestic content. Also, through Polar Racking, when you purchase through Polar Racking, you're not only getting the product that you're purchasing through, you're also getting the site support, right? So we will be there on site, show you how the product gets installed, tricks and tips into how to get quicker, right? Or doing the installation ourselves. If that's part of the agreement, we have the ability to do that. For those that are seeking finance, we have UL certificates and CSA testing as well, and bankability report conducted by a third-party engineering firm, Leidos. So you can confidently go and approach your financiers with the confidence that you are dealing with a bankable solution. Some of our product lines on the fixed steel side, whether it's core flex, is just to serve different markets. Our shield line for carport or Solex for tracker or foundations on any agrivoltaic production, they're all customizable, and that's one of kind of unique or particular about Polar Racking. Is not just the one product, is the product that you need. Now I'm going to hand it over to Jellica for introduction of PRI.
Thank you. So a little about PRI. As mentioned previously, we've worked on over 5,000 completed projects across Canada, United States, and the Caribbean. Our main head office is located in Peterborough, Ontario. And with our recent acquisition of Ecora Consulting, we now have over 100 employees located in 9 offices across Ontario, Alberta, and British Columbia, where we also have our CCIL certified laboratories where we do in-house geotechnical and materials testing. And on the next slide, with respect to our geotechnical engineering team, we do offer a wide variety of services, and we've been involved from the start to the finish for solar development, as early as preliminary feasibility site reviews, and all throughout until the end of construction, where we've also provided some QA/QC support and production testing. And while we prefer to be involved from the start, as there are many different activities that we can offer to better manage your geotechnical risks for your project. And the more we get involved, the more we can tailor the solutions to your site. However, we are able to jump in at any stage as needed and offer you the right solutions. And now handing it over back to Mariano.
Thank you, Angelica. So we thought we'd start with sharing this picture, right? So I think it opens up the floor to what we're going to be talking about, speaking of resilience on cold weather. So with that said, let's see where do we have installation, where we have completed, what is our experience look like. So Focusing on the north, you can see we have installed all across from Alaska all the way to Nunavut. Some of these projects as close as 200 kilometers away from the Arctic Circle, which is typically Canada's northern territories. It's a region that primarily depends on fossil fuels for economic development, for communities as well, and for mining sector. We've been approached through some of these companies, and we're very happy to collaborate to build or to introduce renewable energy into the northern regions. We also have installations along the US and Canada border, different weathers along the East Coast as well, with high wind and hurricane zone prone areas. So different type of harsh weather, then further to the Caribbean into now corrosivity and other weather. But we'll leave this as a topic of discussion for another webinar. We want to focus on this session more into the northern hemisphere, into the northern territory rather, and how do we mitigate and how do we deal with those loads. So the first logical step obviously is understanding your environmental loads. So just at a glance here on this picture, you can see that there's several things going on. There is snow. There's most likely some ice influencing the design, wind as well. Other factors such as topography that may modify your wind pattern and how the wind affects the table design. Other as well, not only what you can see above ground that is evident, but also what's below grade, like frost, for example, right? So with that, let's jump into environmental loads. And the first step is straightforward from the building code. When it comes to wind, snow, ice loads, all this is very black and white prescribed on building codes, whether it's the Canadian building codes or American building codes. They all have similar information, like the map that we're showing here on the screen. There's different intensities, different regions for wind. You'll find the same for snow, ice, and seismic loads and all the rest. So far, everybody must follow the building code. So we're all in the same page. There's no bypass. All the loads are prescribed. All the combinations are prescribed. But it's not only what's on the building code. There are other factors outside the building codes as well. And that's what's important to understand, because these factors also drive the design. We're talking the tools that we have to mitigate the design and factors like topography and corrosion. So let's stick to the tools for a little bit, and the wind tunnel, for example. This is an important tool to have when understanding the loads and the impact, because it's going to determine or dictate how these loads get transferred from member to member all the way to the foundation and eventually from the foundation to the soil. Our wind tunnel studies we have for both type of system that we develop, that we sell, and will allow us to go up to 150 miles an hour wind for tracker structure without instability is concerned, or all the way to the full extent of the maximum wind levels that you can see on the building code when working with fixed tilt. All of these variables are not independent from each other. They're all intertwined. There is a cause and consequence as you apply these variables into your equation. And it's usually for us to achieve our best price, our best design put forward, it's a balance and with regards of optimization with material or with loads or cost. A typical example, if we were to be designing a fixed tilt, where you have a foundation, you have your post, and you have your east-west on top. If we were to put these foundations close together, we could afford to go lighter on the steel for the east-west rails because we have more support, but you end up with a higher cost on the foundation front because you end up with higher foundations on the ground. The opposite to that, if we were to put these foundations or these posts further apart, now you need to compensate by putting thicker east-west to compensate for deflection. So is this balance, this is where experience come in to fine tune this balance, right? The same thing happened with the tilt, for example, when you're trading wind for snow. If you have high wind or high snow, how do you tackle this? Moving the post within the racking to improve moments or to mitigate lateral loads, for example. So these are some of those factors that, in addition to the building codes requirements, needs to be considered.
So it's not always it's not always super straightforward, it sounds like, Mariano, and the interaction between the foundation design and racking design is very apparent. And if not carefully thought out, it sounds like one of those systems could be over-engineered versus the other without, consulting the other professional and, ensuring a balance of loads versus resistance.
Yeah, that is correct, right? I mean, there is that close relationship between foundation and racking. There's no two separate products. There's no two individual designer solving two different problems. We're all focusing on solving the same problem. So I would say that this is a must, right? We need to work hand in hand with our foundation designer to look at every possible solution. Everything has a consequence. Row spacing, tilt on the table, leading edge when it's important. That change the wind effect on the structure. And obviously, understanding from the foundation design, what are the limitations, how much energy we can put or dissipate into the soil through the foundation, and how much energy we can handle above the foundation on the tracker or on the racking itself. It's important. One of those loads, for example, that we're talking below grade is frost. They're not regulated by building code, but they need to be considered. And for this, I'm going to hand it over to Yelica, that is going to talk more into the foundation side.
Okay, thank you. So yes, as Mariano mentioned, an understanding environmental loads is the starting step to doing racking and foundation design. So once PRI enters into the discussion, typically we get all those structural loads from Polar or the racking system, and we do a review of all these loads to understand the load combinations, what the tolerances are. And from PRI, we also consider the ground conditions and how that affects the loading. So one of the largest factors is frost uplift, and we will now talk about the factors that affect frost. So why is frost important? It's because with solar developments, it's different from other conventional structures such as bridges and buildings where those structures have a large dead load. Whereas with solar PV structures, we are dealing with much more lightly loaded structures. So the dead loads are minimal and the environmental loading becomes more of a factor when doing detailed foundation design. And in harsh northern climates, frost uplift is typically what governs over the wind and snow loads from the structural. And this alone carries risk because of the ground conditions. Frost uplift can vary with different factors, even within the same site. And for example, there was one site, maybe a 10 megawatt in Regina, Saskatchewan, where we went and dug out different test beds, and we saw frost vary from 4 feet on one side to up to like 9 feet in another. And that 5 foot of a difference can really impact the foundation design and the procurement lengths that you will have to deal with, especially in solar where we are dealing with hundreds or thousands of foundations and every foot can really add up. And so to back up a little bit here, I wanted to give you a brief recap of what frost is, why is it important. So in a nutshell, frost uplift occurs when there is water between the pores of your soil particles. It freezes, it causes the soil to expand and adheres or bonds with the foundation in the ground. And as it bonds and the soil expands, it causes the foundation to heave as well, or to lift up. And what happens to the racking that's connected to the foundation is it causes differential settlement, especially when there is differential movement between different piles within a single table. And if this displacement exceeds the maximum tolerance of the racking system, then it can lead to failures. And I wanted to give you some more understanding on the different factors that affect frost uplift to really understand why this is a risk for every site, and what affects it. So obviously the first thing, climate. So air temperatures affect the ground temperatures, which causes the soil to freeze. Second, soil properties, whether it's fine-grained or coarse-grained, can really impact the frost penetration. So while fine-grained soils such as clay and silt are more frost susceptible, coarse-grained soils such as sand and gravel can lead to more or higher frost penetration depth because of their higher conductivity. So this is something we would analyze during a geotechnical investigation program. The third factor here is the foundation itself, because frost adheres to the actual foundation. The size of the foundation affects it. So the larger your foundation is, the larger your frost. And one of the things we consider regarding the racking is their restriction on sizes. So because we are intimately involved with Polar, we are very familiar with the size restrictions that they require for the different racking systems. So for example, if we have a single axis tracker, typically we require 4.5-inch OD. If it's a fixed system for single post or dual post, then those are also different sizes that are required for connection to the racking. There's also the shape of the foundations, because different racking systems are built to connect to different shapes, such as it can be a round post or a wide flange beam, depending on what the racking can accommodate. And finally, we also have the type of foundation. So whether the foundation involves just pure steel or if it involves concrete, it does affect the frost load for the design. And since a lot of these can vary, frost uplift can vary as well. On to the next slide. So one of the most common questions we get from clients or contractors is, why are design frost ups greater than what we typically see? When you go and dig an excavation, why do I only see 2 feet of frost, but why does your drawing say 4 or 6 feet? So one, we talk about site variability already, so obviously that's a factor. 2, seasonal fluctuations, and this is typically out of our control. The third factor here that I wanted to bring up is design life. And for solar projects, it ranges typically from 25 years to what we've seen 40 years as well. So the longer your design life is, the higher the return period that the designers use to calculate frost penetration depth, due to the higher risk and the lower probability. Another factor is the safety factors. So depending on the site location and the jurisdiction, the engineers have to adhere to the code, and we use the recommended resistance factors for geotechnical design, and there's also load factors for structural loading that are applied to the frost depth. And the final factor here is warming. We all know warming's a thing, and it's becoming more imminent in design considerations, especially in applications such as in the Arctic. And at the moment, there is still a lack of guidelines on how to deal with warming effects, but it is slowly becoming more prominent, and we are developing tools to better understand how to include warming effects in the calculations. But currently, we do rely on most recent historical data as opposed to climate warming models, which in itself carries its own risk.
It's,
Yes, Arash.
if we're looking at, which looks like maybe you're going to tell us a little bit about this now, how does some of those different parameters impact the frost depth? So, looks like you're a step ahead of me, so go
Yeah.
ahead, Jellica.
Well, thank you for the question. That's perfect. So on this slide, as I mentioned, we prefer to just do the manual calculations ourselves to determine what the frost depth is for a site, because there are a lot of factors to consider. But there are other tools that are available, such as published mapping. So here's an example of available maps where you can just go find your location and it will tell you what frost depth is for that location. However, it does require you to understand what the assumptions are carried in developing those frost depths, because it can highly vary. So here in this map, for example, we have a 25-year return period. So for this example site, let's say we have ground that's covered with sod conditions and also covered with snow conditions. As both of those things act as an insulator, for a 25-year return period, your frost can be as low as just 1.5 feet. But as soon as you change those different factors, like if you remove the sod condition, it doubles to 2.3 feet. If you remove both, including the snow, then it goes up to 5.7 feet. If you change the return period to allow for a longer service life, then you're now seeing 6.6 feet in frost. And this is just an example of how very small factors can affect your frost depth calculations, and it really requires a deeper understanding of what factors affect frost and what is applicable or not applicable to your specific site. And why is this important? Again, because it directly translates to pile lengths. If you have a 5-foot difference in frost depth, then there's a 5-foot difference in pile length that you can save up if you're not really optimizing the conditions to what the project requirements are. And furthermore, there is also a risk on the owners in the long term, because if an engineer assumes bare conditions without sod, without snow, then it is on the owner to maintain those conditions for the design life of the facility. And these are all risks that need to be well clarified and communicated from the start.
From the structural standpoint, at first glance, things seem quite straightforward. However, as Mariano shared with us, a lot of these assumptions can drive a lot of different loads to the foundation. Then we consider frost penetration depths, the potential variability in external conditions that are beyond our control seem to really have a large impact on the frost penetration depth, which can really increase the foundation type. And typically, what are we seeing happen as we increase the frost penetration depth for a certain foundation, Jellica?
Here, like you can use this example here right now. So this slide shows you a couple of the most common foundations we utilize for solar development. So we have ground screws, drivens, micropiles, helicals. They all have different considerations when it comes to designing for frost. But maybe the simplest example I can give you is for the helicals and ground screws. So both of those options rely on capacity generated from the end bearing helix plate or the threads that are at the bottom 2 or 3 feet of the pile. So when designing for frost, we want those plates or threads to be below the frost depth for starters. There are other considerations, but the minimum is to have those below the frost. So if you have frost at 2 feet, then your helix and ground screw would need to be below 2 feet. If it's 5 feet, then it has to be below 5 feet. So there's a direct impact of the frost penetration depth, and the deeper you go, the deeper the piles will need to be.
Okay, so some of these assumptions, although maybe it's advantageous to drive the frost penetration depth lower, there's ultimately some risk associated with having to maintain it. So how do we strike a balance between the depth and the risk and the overall load that we're generating?
So that comes in with a clear understanding of how to develop the frost loads. There is a method that we follow that has been published by Becker in 2016, where you look at frost from two ways for two methods. I'm not going to go into detail there, but it considers the probability of the maximum frost depth occurring versus the mean frost depth occurring and assigning the different factors of safety accordingly so that you're finding that optimum load as opposed to just assuming the worst case frost for the worst case climate for the worst case of everything and then applying a factor of safety there. So there's some engineering skill that you need to consider there without doing too little, but also not doing too much.
Okay, so striking a balance.
Yeah.
And of course, we need to do this all while considering the racking conditions.
Correct.
And so Mariano, where do you see as one of the number one places where, potential complications happen between the structural and foundation engineer as we deal with the superstructure and the foundation?
Yeah, I mean, it's key for both parties to understand the limitations of or both on both systems, I should say, right? If we're expecting to have settlements, what do we have above the racking to deal with settlement on the racking side of things, if it's going to happen? What is the strategy to mitigate that? So we need to include adjustability features post installation, so we can deal with those as they show up. Deflection is another factor. If the deflection on the foundation is exceeded, now your wind load parameter as calculator is changing. And you can potentially fall into a situation where you underestimated load. Just to mention a couple of the factors.
Right. Okay. Just going to our Q&A here, we do have one question that I think the first question I think we're going to actually answer in one of our case studies, so I'll leave that for now. But just before we move on from frost, we got a question here that says, how should foundation design change in regions with deep frost penetration and repeated freeze-thaw cycles? So for clarification, repeated freeze-thaw cycle means periods where the soils go above zero and below zero, and these are actually the worst potential conditions for foundations. Typically, you're going to see this in the fringe seasons around spring when we're transitioning from winter to spring, and you've got repeated cycles of freeze thaw. So the temperature is going above 0 degrees Celsius or 32 degrees Fahrenheit in the day, meaning that we're having thawing occurring. Also, as that's happening, typically you're seeing snow melt. And as the snow melts, in a lot of cases, because the ground or the surrounding environment is frozen, there's not proper drainage relief. And so what happens is the water sits in pools at grade. And in a lot of cases, we're percolate into that thawed material. And in order to have frost uplift, you need three conditions. You need cold temperatures, you need frost susceptible soils, and you need water. Eliminate one of those three items and you substantially reduce the potential for frost uplift. When you have those conditions and those repeated freeze thaw cycles, you're typically seeing all three of those conditions happen at once. And that's where the amplification of frost loads really does occur in the winter. So some strategies that you could use to alleviate some of these concerns is a lot around O&M, making sure that if you've got a site that it can drain properly, even intermittently in the winter. So that might mean you need to do some snow clearing, some snow removal, just to clear access ways to some of the ditches. Alternatively, you just need to consider your full frost loads. So, you do a more robust design, or you look at a more robust O&M process to protect your systems against that. And we actually have a question here, which I think you've got a slide on next, Jellica, on how does the design process differ when we're dealing with permafrost?
It's like I designed that question. Thank you, Nima. So the next slide here actually addresses that. So one of the other foundation options that were not listed on the previous slide is for permafrost sites. So in the Arctic, where we do anticipate permafrost, we use adfreeze foundations or adfreeze piles. It's basically consists of an oversized pre-drilled hole where you place an adfreeze sand slurry around the annulus of the pile. And the idea is that we are relying on the adfreeze strength, which is the bond between the permafrost and the pile, to provide resistance to the environmental loading. So the shallower the permafrost, the better. But if there is shallow bedrock, then we also can use micropiles as a foundation solution. Is there another, I think there's another question on permafrost as well. What foundation strategies work best in permafrost, expansive soils, or seasonal unstable soil? Okay. Do you want to take on the unstable
Sure. Yeah, I can
ground
talk
there?
about
Okay.
yeah, I can
Yep.
talk about expansive soils and seasonal unstable ground. So we don't see a lot of expansive soils here where I am in Ontario, but they are something that's common in Western Canada and Southern United States. So expansive soils are typically swelling clays, and so you would want to do a swell test to verify if that's a concern or not. Once you verify if it is expansive or not expansive, designing for this is very similar to frost uplift. Frost uplift is a parallel force to the foundation shaft, and very similarly so is swell. So you're designing them both with the same strategies. So some of the strategies that Jellica discussed earlier as we relate to frost uplift resistance would apply to expansive soils as well. When we're dealing with seasonally unstable ground, two things come to mind. One is unstable grounds from a stability and excavation standpoint. So in a lot of these cases, you would typically wanting to be doing foundations that don't require a boring to be completed, which works out very well because the most commonly used foundations in these types of applications is a driven foundation, which 95% of the time will not require pre-drilling. The alternative to that would be helical foundations, which once again does not require a pilot hole to be completed. The other consideration there when you're dealing with seasonally unstable grounds makes me think about wetlands or in sites where you've got a low groundwater table. When you've got a low groundwater table, it typically will result in having a low lateral capacity. So if we have this condition, it may be appropriate to do lateral testing, particularly in that seasonally unstable ground condition. So probably once again in your spring season where your lateral conditions would be, your lateral resistance would be lowest. The one thing to keep in mind when you are dealing with lateral resistance design is that one of the beauties, well, it depends on the racking system, but a system like Polar's, where they use short tables instead of long rows, you have a higher probability that the foundations in a single table are going to act the same. And as long as the foundations are all acting the same, it means you're not transferring any of that stress to the superstructure. So movement is acceptable. In fact, anybody that tells you that a foundation is not going to move probably has not seen long-term performance of foundation. It is impossible for a foundation not to move in any capacity, whether that's even just a couple millimeters or, quarter inch, eighth of an inch, there will be some form of movement regardless. And as long as that movement is uniform, it's not as concerning for the racking system.
I think there's one more question regarding permafrost before we move on here. What methods have you utilized for foundations in permafrost environments to ensure that the foundation doesn't conduct heat to the ground and begin to thaw the permafrost. So think there's several factors here, but without utilizing special techniques above ground, one of the ways we do this is to ensure that the frozen slurry is also placed within the inside of the pipe. So you're creating the frozen material inside and outside to limit the heat on conducting below ground. Is there anything else you can think of there?
Yeah, I mean, just real
Arash?
quickly, we also consider typically when we're working in permafrost regions, we consider some degradation of the permafrost. We
Yeah.
do add a factor of safety. It's in response to kind of this condition, but also the potential for change in temperatures or ground thermal conductivity. One thing to keep in mind is when you have a native undisturbed site, it's typically a lot more insulated than when you introduce sands and gravels. So the artificial change in the site can have a negative impact. And so we add usually a half a meter or a meter buffer to our designs in these regions to consider that.
Okay. I think we'll move on now in the interest of time to the next slide here. So over to you, Mariano.
Thank you, Angelica. Thank you, Raj. That was certainly interesting and very detailed about foundation. Now let's learn a little bit about how do we deal or how do we mitigate these loads above ground on the racking itself, right? What can we do to alleviate the problem? So starting from wind, we're dealing with high winds, very common sense. If we go with a shallower tilt on the racking, it's more aerodynamic to the wind, it shed more of the wind loads, and we result on less foundation or less reaction loads into the foundation. The opposite to that is when we have loads like snow loads and ice loads, right? So now they are vertical loads, and the more that we increase the tilt, then the more that we facilitate the shed of the snow when we're talking snow in particular. If we have both, then we'll see a bit of a case study later on. But there are other means to mitigate, right? To deal with wind, we can look at the deflection aspect. If we have no choice but to choose one, either wind or snow, we need to then deal with deflection. And do we brace components? Where do we brace them, right? What is the right spot to achieve the control deflection on the racking? Moving the post back to front will have an effect or a trading effect between moment reactions and between lateral reactions. So understanding from the foundation point of view, like Jellica and Niraj were explaining earlier, understanding those limitations, we know where we can move, and then we react accordingly. So we did talk about that, the ability to customize that's key so you can mitigate your loads. We talked about the synergy between polar racking and PRI or foundation design and racking design. This will allow us to assimilate more knowledge, understanding each other, product each other part of the equation. These translate into adding robustness into the system, which equate to obviously a stronger solution that is absolutely needed when dealing into the north. We've been building on the north for quite a bit, so we gain experience. Moving into resilience, so how do we make it more resilient? Well, the formula is very straightforward. We listen to our customer, we listen to our installers, what do they have to say about our products, and we update, evolve, implement, and go to the next, basically. We'll have a few examples here. If we're talking about adjustability, well, the first thing that you need to have on our system is the ability to install. If it's going to become too difficult to install, if you don't have the right level of tolerance or adjustability features, it's not a solution. From there, our initial racking design was based on direct bolting, which is very, very efficient when you're dealing with high winds and making sure that the module is not going to fly over. But it's very difficult to manipulate small fasteners with gloves when it's cold. So we include top clamps as a solution in our portfolio. Top plans are very good as well, reduce the number of fasteners that you need to put in, but there are other solutions as well. What if you want to go further, right? So now we're looking into V-clamp options, which basically what we're doing is clamping the bottom flange on the module into the rail. Now this is much easier to install, and it's more in tune with the requirements of the northern latitudes. Same story goes over and over, feedback from our customer. We're using the purlins as a tray, and there is water accumulation on the tray where you have cables as well. So water management hole, this is straightforward. We put them in place, we put draining holes, we deal with water and ice when we're working into the northern latitude. We go into fasteners next, right? Details as simple as using serrated fasteners that allow you to torque fasteners using a one-side tool on one side of the fastener. You don't need a backing wrench anymore. These facilitate and expedite the installation. The next is compatibility with foundation. So as we go through all these problems, we're incorporating more solutions into our system. Developing on the north is not an easy task. And imagine not only the design, but the logistics of it, right? If we're designing for a ballasted foundation and now we need to bring concrete to a remote location, that could become challenging. Some of the sites that we have developed in the north, they're only accessible through winter roads. Literally, we're driving over a frozen lake to get to the site. So having the ability to work with gabion basket, and this is where gabion basket was introduced as a solution, because a lot of these mining sites have lots of availability on rocks. As a subproduct of the operation, we can use these to ballast the system. So the key takeaway here is good engineering doesn't slow down installation. It doesn't add cost to the installation. It's there to solve the problem, is there to make the installation faster. With that said, we have our first case study here. This is a project that we did in British Columbia, Clayoquot, British Columbia, where we have 0.32 kp of wind. For those using the American Building Code, assume average around 90 miles an hour. And I know the units of measurement is different. One is hourly and the other one is 3-second gauss, but roughly that's what equates if we were to be talking in terms of American Building Code. So, and that was about the only good news that we have about this site, because everything else went downhill from there. No snow, very high. Rain by itself is not that high, but it combines with snow. It changes the density of snow. And when you're changing the density of a big number to begin with, you're ending with a much bigger number. And to make matters worse, suboptimal soil conditions. So what do we do here? The first thing that we do as we understand the geotech from PRI studies is that we have a soil that is not strong enough. We need to tackle this with a dual post system. The moment that we set ground screws, PRI knows right away, okay, this is a 3.5-inch diameter. And from that, we get the capacities and the limitations. So we can take this much moment, we can take this much lateral. We do our first iteration and understand where we're sitting. Too much compressive loads failing the foundation, that we increase the tilt to mitigate snow. And we deal with wind later as we go through the problems. And then we see foundations, right? We have now one of the foundation, the front foundation, it's under capacity, can take more load. The rear foundation is over capacity. So you just redesign the brace or change the brace between the posts to improve load sharing between the two and solve the problem that way. We said that we'll deal with wind as well. So we go to our wind tunnel and we understand what are the areas that are affected by wind. We have no choice but increase the tilt, because otherwise we're going to be failing foundations or exceeding the foundation capacity. So how do we deal with wind? So one of the unique features that we did on this site, as you can see on some of the pictures back there, that the post spacing on the table is not constant. So we identify the area of concern because of wind. We reinforce that area. We don't need to spread that solution across areas of the site or of the table that are not affected by wind. And that's how we solve the problem. So it's having that open mind, that ability to go back and forth between foundation designer and racking designer to understand each other problem and limitation and what are the recourse that we have to tackle. Very quick, I'm going to touch bases in O&M. There are tasks that is required as part of the O&M. I mean, we can design a very strong, robust solution, but it needs to be maintained because these systems are there for the next 20, 25, 30 years, depending on the requirement. And we need to survive that time frame. So tasks as simple as doing annual site inspection, to be on the lookout for torque checks or some corrosion spot that could be developing is important to keep the structure resilient and robust, but also not only maintenance, but also on the cash flow, on the gain. Simple fact as cutting the grass improve the albedo effect on the site, and now you get a much more improved bifacial gain from the back of the module. And with this, I wanted to jump into our second case study. So we've been talking about foundation designs. We've been talking about racking design, interaction between polar racking and PRI, how we mitigate, how do we share with each other to solve the problem the best possible way. But the most important question is, does this work? Everything that we talked about today, does it yield good results? So let's explore this together. So this is a site that we built in Prince Edward Island, Canada, Summerside. PRI was the foundation designer for this site. Polar Racking was the racking designer. We went with the normal package with the geotech, foundation design, racking design, foundation test, and installation support. Half of the site was built, half of the site was still under construction. At the time, September 2022, Hurricane Fiona strikes and reached the east coast in Canada. High wind, devastation, housing, buildings, electrical infrastructure was not spared, neither were solar farms. So when we look at the aftermath of the event, polar racking, no issues. There were a couple instances where modules came off the racking on the area that was under construction because they didn't got to the torquing extent yet. But other than that, no issues. And when we look at sites from our competitor, this is what we get. One of these sites is Nova Scotia, and the other side is on the vicinities of our Summerside project that we developed. So this is an indication of what can happen when you design without taking all of the loads into consideration, whether it may be frost or whether it may be foundation strength or racking deflection. If you don't check all those boxes, you may end up in situations like this that neither the racking manufacturer wants to see something like this, or the customer, or the owner, or the foundation design. This is undesirable across the board. You could say, okay, maybe we were lucky. We got spare. Okay, let's dive in deeper, right? This is the path of the hurricane at the time where it crossed through eastern Canada. The range that where it went on the middle picture there in black and white with the green dots, you can see on all the areas where we have installations, not only the case that we're looking in Summerside, but other locations in Halifax as well, and New Brunswick. None of the sites got affected. All of the site got exposed, but no damage to the site. So answer the question, does it work? I'll let you read through these communications coming from the owners of the site, from the developers of the site. And as a racking manufacturer and as a foundation designer and manufacturer, Is very refreshing to hear this type of feedback, not because we're surprised that it worked. We know that it's going to work. We know how we design things. We understand our structure, but it's good to get acknowledged, to get that publicity, to understand or hear from other people what is their opinion to our products, right? So the takeaway is whatever we're selling here today as a solution, does it work? And is worth it. Right? And with that, we have reached the end of what we were planning to share with you today. I'm going to hand it over again to Arash to open the floor for questions.
Yeah, so we did run to 3 o'clock. For those of you that want to stay and ask questions or get some of the answers on some of our questions, more than welcome to do so. But I think in conclusion, for those of you that do got to run, hopefully you understood the importance of hiring qualified professionals, both on the structure and foundation side. What might seem like a very straightforward structure can become very complex because of the sheer magnitude of the size of these facilities. And it actually kind of makes me think to one of the questions that was asked here, which was, what construction techniques and scheduling strategies can minimize risk when installing foundations in frozen or remote conditions? And planning, planning. Not giving yourself the opportunity to do pre-construction installation and tests could result in over-engineered or under-engineered foundations, or just foundations that are not suitable for your site conditions without having an understanding of how construction techniques will behave prior to construction. It may result in having to employ more expensive construction techniques. And for many people, this is a little bit confusing because in any other type of construction, this isn't a concern. And the reason, once again, is because of the sheer volume of foundations. PRI is working on a project in Canada that has 165,000 helical foundations. If each one of those foundations take an extra 2 minutes or 5 minutes to install, that could result in a very, very large impact to the overall schedule. So getting an understanding of how these foundation elements behave and what the ease of installation is, what will be the challenge during construction. When you're dealing with this sheer volume and this sheer size, you will have some complications. And having a foundation engineer and a racking engineer that's in sync and understands the limitation of both systems is critical for a successful project. We will just go through a couple questions here. We will try to maybe wrap this up in another 5 minutes, but there's a question, can you also perform calculations to provide annual solar generation and the difference in numbers while using different types of racking system, taking in account the soiling losses due to snow accumulation and frosting? You know, we are civil engineers, structural engineers, geotechnical engineers. We do leave the modeling for electrical engineering professionals. That being said, we do have partners that we can team up with to undertake that, and we can definitely provide input as it relates to some of the assumptions for soiling loss or other types of losses for the system. Maybe this next question I'll ask Jellica. If you allow the structure to float in the deep frost zone, do you have to allow for more tolerance in your tilted frame design?
So typically we would design the foundation to be below the frost zone. Otherwise, the full superstructure and foundation will be subject to frost uplift. Now, of course, there are cases where we do have really deep frost depths in the north, and this is where some frost mitigation strategies can be considered, such as sleeves or insulation and other ways that we can provide you options for. When it comes to tolerances from the racking system, and of course, this is something we always consider. We would model the different foundation types or different strategies and consider how much deflection we would be expecting. And as we receive the tolerance limits from the racking structural engineer, that would give us more flexibility to choose the right option that would allow for less deflections than the allowed tolerance.
Yeah, and I would like to add to that as well, post adjustability features. Like once the system is installed and you have no choice but to deal with frost heave or settlement, having the ability to adjust the post, although that involves O&M, but that's one of the solutions, or on the last of the solution, I guess, that you want to tackle, but is there on the table.
There's another question about ballasted systems. Are ballasted systems also considered suitable for cold areas, or permanent foundations are the preferred option? Either can work. From a cost standpoint, typically permanent foundations are a lot more cost effective. Going back to our list of questions, how do extreme snow loads, drifting patterns, and high wind? I think we actually already answered this one. So how much longer does it take to install piles into bedrock? What is the most challenging ground condition to install piles? I don't know if you want to take that one, Jellica.
How much longer does it take to install piles into bedrock? It depends on the foundation type. So there are variable bedrock conditions, from soft weathered sedimentary bedrock to the harder types of bedrock. And depending on how soft it is, the foundation type could range from driven piles to bedrock micropiles. So if we're dealing with driven piles, there's various pile driving techniques to consider there. With micropiles, it involves having to pre-drill a hole, placing the concrete, and then placing the pile. So there's a lot of factors to consider here, and it depends on what type of bedrock we are anticipating and how deep it is.
Okay, so in a nutshell, that's probably one of the more harder conditions.
Yeah.
How do you handle cases where the wind load exceeds the rating of the PV module? Utility scale projects typically want to avoid the smaller residential modules that have the adequate rating. That's probably for you, Mariano.
Yeah. So we have designed a lot in the Caribbean as well, where we're designing for 150 and 180 miles an hour winds. And direct mounting is the typical solution for that type of installations when you're exceeding the module pressure. Unfortunately, there's not much on the racking side that you can do other than adding more structural members to add additional support. But that is driven by the module itself. There are modules that are more into the Caribbean market that have reinforcement. Obviously, it's smaller in size, so the wattage output is not the same. They're more suitable for higher pressure. If we're talking the regular utility scale, you mitigate for as much as you can by changing the tilt, so that lessens the pressure on the module going shallower, but it will also have a consequence on your energy production, right? So it's all a balance, right? Where am I going to be better off as a final picture? Give up a little bit of energy production for safer longevity on the modules, or increase your structural steel and add additional members to support modules on multiple spots.
It's all about balance. I think that's probably a great place to end things. Thank you very much, everybody, for joining us today. Our contact details are below for those of you that want to get in touch with us to discuss about future projects. And hopefully after this session, you realize the foundation and racking system interaction is quite important, and the impact that the lack of familiarity between the two designers of these systems could impact the overall system. Thank you, everybody, and looking forward to opportunities and working on some projects with you all.
Thank you, everyone.
Thank you, everyone.